Our next talk will be presented by Glenn Mevel, who will be presenting a concurrent separation logic for multi-core OCaml.
So welcome to this talk. I'm Glenn Mevel, and with Jacques-Henri Jourdan and François Potier, we've been working on a concurrent separation logic for multi-core OCaml. What does that mean? Our aim is to verify fine-grained concurrent programs in the setting of the multi-core OCaml memory model, which is a weak memory model. In this talk, I present a concurrent separation logic with a notion of views. So a few words about multi-core OCaml. As the name suggests, it is an extension of the OCaml programming language with support for multi-core programming. It comes with a weak memory model, which has been formalized in a paper at PLDI 18, and it features two flavors of locations, which are dubbed atomic and non-atomic. By the way, if you're interested in the garbage collector of multi-core OCaml, please have a look at this other ICFE paper whose title is Retrofitting Parallelism onto OCaml. So what is the challenge here? Essentially, the challenge is dealing with the weak memory. Under sequential consistency, traditional concurrent separation logic gives you a points to assertion, x points to v, which expresses your unique ownership of the memory location x, and which also says which value is stored in x. And then you have the usual Hoare-style rezoning rules, and this assertion gives you ownership of x, but you may want to share this ownership among all threads. To do so, a usual solution is to put the assertion in an invariant. Intuitively, an invariant holds at all times, and its contents can be accessed equally by all threads. So here, we can put x points to something in an invariant, which we denote by boxing the assertion. Then any thread can access x as long as it preserves the invariant. Now, what breaks under a weak memory model is that each thread now has a different view of memory. This notion of view is crucial because it means that some assertions, like the points to assertion, are only valid with respect to the current view of the thread. We call these kinds of assertions subjective assertions. But on the other hand, invariants hold equally for all threads, so they can only contain objective assertions, where by objective we mean non-subjective. Then, the challenge is to keep a program logic which feels simple and natural enough, but at the same time is able to deal with subjectivity and allows subjective assertions to be shared between threads. I just spoke about the view of a thread and how it is central to the challenge of weak memory, but I haven't defined this concept yet, so let me do that now. Because of weak memory, each thread only knows a subset of all writes that have happened to the shared memory. This affects how the thread reads and writes the memory. For example, once it has learned about a write, it cannot read from earlier writes anymore. This is an example of what a weak memory model would say you. And this subset of write events, we will call it a view. So the view of a thread, is the set of the write events it knows about. Now we want to manipulate these views from the logic. For that, we add new kinds of assertions. The first new kind of assertions is this upper row u, where u is a view. We pronounce it as we have seen you, and it means that the current thread knows all writes in u, so it is an assertion about the current view of the thread. And the second u assertion is p at u, where p is an assertion and u is a view. It means that p holds in the eyes of any thread which has seen u. For example, let's say that p relies on knowing a given write event. Then it requires the current view to contain that write event, so certain p is subjective. But instead, we can assert that whatever the current view is, if it contains that write event, then p holds. And by saying this, we do not depend anymore on the current view, so saying this is objective, even though p may be subjective. And that's what p at u means when u contains the given write events. So we can make a subjective assertion objective by specifying the view at which we see it. And why is it interesting? Because these new assertions are complementary. More precisely, in our logic, an assertion P is equivalent to an objective assertion. Any assertion P is equivalent to an objective assertion of the form P at U, and an assertion of the form upper row U for some view U. This shows in particular that view assertions of the form upper row U capture all the subjectivity of the weak memory, and this decomposition will allow us to share subjective assertions between threads by using a different mechanism for each part. The first part, P at U, is objective, so it can be shared via an invariant, just as in usual concurrent separation logics. Regarding the second part, sharing upper row U means exchanging information about write events between threads. So in other words, it means synchronizing. So we will rely on some form of thread synchronization that is provided by the memory model. That was the main idea of this talk. Now I show you what is in our program logic to reason about programs in memory, and I'll start with the simplest thing, which are atomic locations. For atomic locations, we have a neutral looking points to assertion, atomic x points to v, which means that, that we own the atomic location x, and x stores the value v. We are able to say such a thing because atomic locations in Monte-Carlo behave in a sequentially consistent way. At any given time, all threads see the same value for x. In particular, this assertion is objective, then it should come as no surprise that atomic accesses obey the usual hot triples, both reads and writes. Where things become interesting is for non-atomic locations. The non-atomic locations of Monte-Carlo have a relaxed behavior. In our logic, we still have an assertion x points to v, but its meaning differs slightly. It still asserts the null shape of x, but instead of saying that the value of x is v, it says that we have seen the lattice right to x, and this right bears the value v. And this is the typical subjective assertion. There is no such thing as the global value of x because different threads do not necessarily know about the same rights to x. What is really nice with this points to assertion is that it also obeys the standard rules, so we have a simple looking assertion that behaves in a natural way. The price for it is that the assertion hides more behind the skins and it is subjective. So we cannot share it only by using an invariant. So let's see how we can share it nonetheless, and for that, let's consider the typical code pattern, which is called a spin lock. Let's say we have several threads that want to access the same resource, such as a single non-atomic location. Then we can use an atomic flag to guard that resource. When the flag is true, the resource is taken, and if you want to acquire it, you need to wait for it to become available. Now, from a logical point of view, the lock can be seen as guarding an assertion P, which may be subjective. For example, it may be a non-atomic points to assertion, as we have seen just before. The first thread has P before releasing the lock. The second thread will get P after it has acquired the lock. So we want P to be transferred from the first thread to the second one. To see how that works, let's consider only the concurrent set operation that succeeds, because that's when the transfer happens. As we've seen, we decompose P into an objective part and a subjective part, so that we can transfer each part. The first part, P at U, is objective, so it can be transferred using an invariant as usual, so we get rid of it. So now we are down to the problem of transferring a view assertion. As I said before, we need some form of synchronization, and here, what Monte-Carlo gives us is a happens before relationship from the release write to the acquire read. So instead of adding new primitive to the language, Multicore Camel made the choice of performing release-acquire synchronization on atomic accesses. And we need to reflect this in our program logic, and we do so by extending the atomic points to predicates. So recall that atomic points to V means that X stores the value V. We now extend this assertion so that atomic locations stores the pair of a value in the view. So accesses still behave the same with respect to the value, but they also perform a release-acquire synchronization on the view. So when writing, we push into the shared location any information we had in the local view, so that's a release write. And conversely, when reading, we pull into a local view any information stored in a shared location. So that's an acquire read. And with this in mind, let's come back to our spin lock. As we have seen before, the spin lock has two operations, release and acquire. In the interface, it works in assertion P. We give the spin lock a specification, which holds under some invariant. And now, to prove this specification in the usual separation logic, with sequential consistency, we state an invariant like this. We are either locked or unlocked, and in the latter case, the invariant itself holds the assertion P. Now, in our program logic with weak memory, P may be subjective, but everything in the invariant has to be objective. So the invariant we state instead is that one. In fact, it is the same as in usual separation logic, but we add views. To remain objective, we make it explicit at which view we have P, and we say that it is the same view as is stored in LK. In other words, P holds in the eyes of whoever last released the lock. So the P at U in the invariance obviously allows to transfer the objective part of P, while the atomic location itself allows to transfer the subjective part of P. So that was the proof of the spin lock. And in addition to this example, we did more case studies with different kinds of locks, algorithms for mutual exclusion. And in all of these examples, we have been experiencing the same pattern of sprinkling views over our invariants. So a general method for proving the correctness of a concurrent data structure is to start by reasoning as if we had a sequentially consistent model, express the invariant in the usual concurrent separation logic, then identify where synchronization happens and make it explicit by adding views. To sum up, I have presented a program logic for Multicore Camel based on isolating subjectivity into views. I argue that this logic enables concise and natural reasoning about how threads synchronize. There is more in the paper, namely how the logic is realized by building on top of a lower level logic, and we also have more case studies. This entire work is mechanized in the Coq proof assistant using the Iris separation logic framework. So we have a verified proof of soundness on the Tile language with which we can write programs and prove them correct under using our program logic. And in the future, we would like to verify even more data structures, and also we would like to investigate data races. Because data races are currently not supported by your logic, even though the underlying memory model gives a few guarantees about them. Thank you for your attention, and if you have seen our previous slides, you hold the right to ask questions now.
Thank you, Glenn. If you are watching this talk live as an ITCFP participant, please look to see if there is a Q&A session available so that you may discuss this work with the authors of this paper.